Hello. So another video. Today we're going to do the topic of calculus, where we find the maximum and minimum of certain problem-solving questions. So I call it Maxima Minima. If you were to trawl through a number of advanced past papers, it's generally one of the last questions, if not the last questions in the exam. So it's generally considered to be one of the hardest, if not the hardest, topics in 2-unit. So I thought I'd give you a framework today on how to deal with these questions and then go through a few myself. So a few worked examples. So topic is calculus Maxima Minima. So basically, if you go through these questions, generally speaking, there are two parts to the question, part 1 and part 2. Part 1 is normally 2 to 3 marks, and part 2 is about 2 to 4 marks, depending on the, intensity of the question itself. So part 1, normally the question would basically ask you to prove an equation, right? This is so prove or find the equation, and I'll put in brackets, to differentiate, because this part is to set you up to do part 2, right? So I guess when we do these questions later on, I'll highlight it to you then, but for now, it's really important for you to see if this question was 2 to 3 marks for part 1 and 2 to 4 marks for part 2. If you can't do part 1, you can still use the solution or the equation that they give you to do part 2. So a lot of my students, I say to them, if you can't do the first part, don't be silly. Use it to do part 2 and get the second part's marks, even though part 1, you might lose some there. Now, to prove this, generally speaking, we have an equation or an example that might have 2 variables on the right-hand side. So for example, they might say, volume equals to pi r squared h normally. All right, let's talk about the cylinder, where r and h are the 2 variables. Now, in 2-unit maths, it's very hard to differentiate when there's 2 variables at play. So what they give you instead, normally the game that we need to play here is that we basically make h, some sort of function, let's say 3r, and then you sub this back into here to get an expression that we can differentiate where there's only 1 variable at play. So it might be like pi r squared 3r, which we get as 3 pi r cubed. And then we differentiate this. Yep. So in part 1, it's all about finding the relationship between, if there's 2 variables, finding the relationship between the 2. So then we can sub 1 into the other to make it only 1 variable, so we can differentiate. Now, which leads us nicely onto part 2, where once we find it, we're gonna find the max or min. And to do this step, there's generally 3 parts. The first part is to basically, differentiate equation in part 1 and solve. That's crucial, right? To find the maximum minimum, yeah? And then we need to test for max min. So just like curve sketching, when we're testing for to find whether it's a maximum minimum stationary point, to do maximum minima, we basically test where use the second derivative if it's easy to differentiate, or if you can't, use table method. If it's a fairly lengthy or difficult equation to further differentiate, use a table method. And last but not least, it sounds pretty obvious, but answer the question. And by that I mean, sometimes it's asking you to find the value of r, sometimes it's asking you to find the dimensions, sometimes it's asking you to find the actual maximum volume. So answer the question, because it's very easy to, stop short of getting the full marks. So this is basically the framework that we're going to use to do these maxima minima questions, which is generally considered to be the hardest part of tutor maths. Let's go. So I've prepared a few questions. The first one is a relatively straightforward question from the HSC 2010. I just want to highlight to you the framework and how it applies, right? So you can see, once again, two marks. So 2 parts where there's 2 marks for part 1 and 3 marks for part 2. The word minimum value there. So if you basically did a search of the word minimum or maximum in past papers for the last, I don't know, 10, 20 years, you generally find one question, and that question is generally near the back, right? So, and that is a maximum minimum question. And you can see 5 marks, right? Pretty chunky piece of the test. So look at part 1 now. Let's apply the framework to that. Part 1, they give you an equation for the surface area of a cylinder, and it's got 2 variables. It's got R, and it's got H. Yeah, so we can't differentiate that in part 2 when there's 2 variables. So instead, they ask you to prove an equation where there's only 1 variable, R, at play. So what that means, we're probably going to find an expression for H in terms of R. And that piece of information given in the question is here, where it allows us to say volume is 10. And if we express volume in terms of R and H, we can make H a subject, right, to sub it in. So that's the game plan. We're going to start off with the volume and then sub that value of H, which is in terms of R, into this expression here to get that. Once we get that, the framework basically says differentiate, solve, test for max min, answer the question. So let's get a move on that. So we know volume equals to pi r squared H for a cylinder. And in this, sorry, pi r squared H, I said it, but didn't write it. Pi r squared H, and that equals to 10 in this question. So I'm going to make H the subject in this case by dividing the pi r squared over. And I now have an expression that I'm going to sub into the surface area formula that they gave me, which is pi r squared, 2 pi r squared for the 2 circles on top and bottom, plus 2 pi r h for the curved surface. And I'm just going to sub this into this value of h, and I should be done. So let's see, 2 pi r squared plus 2 pi r, 10 on pi r squared, and there it is. You can sort of see that the pi r's cancel out, 20 on r, exactly what I want. Therefore, area is 2 pi r squared plus 20 on r, and that is the equation that I'm going to use to differentiate for part 2. That's 2 marks. Part 2. Now let me just read the question. Show that A has a minimum and find the value. That's what I'm talking about when we say answer the question. So it just wants me to find the value of R. So pretty easy. Once I differentiate and solve, test for max min, the value of R that gives us a minimum is our answer. So for the next part, dA, dr, so differentiate that. Now, keep in mind that 2 pi, in this case, is a constant. So bring down the 2, I get 4 pi r. This guy here, if I was to re-express that with a negative index, just to make my life a little bit easier. So bring down the -1, becomes -20 r. -2 minus 1 from power. Yeah, so let me clean that up slightly. Is equal to 4 pi r minus 20. Bring down the negative index to make it positive. And guys, that is my derivative. Yeah, this guy's my derivative. Now, it looks pretty simple. So when I go on test for max min, I reckon I'm going to use a second derivative. So let's carry this forward. So differentiate, solve, test for max min, answer the question, right? So when I set this to 0, bring the fraction over the fence. R squared, maybe times the R squared up, divide the 4 pi down. What's that? 5 on pi. And then I know that R equals to cube root of 5 on pi. Yeah. Now punch in the calculator, maybe do it to 1 dp just to get that value. What is that? So, oh, sorry, I said cube root, didn't I? So cube root that, 5 on pi. I think the answer is about, so it doesn't say 1 dp, or maybe I'll do it for myself as 1.1. I'll do it to 2 dp maybe, as 1.17. Now, once I do that, got the value of R, test for max min, answer the question. So I'm almost there. Pretty straightforward. So I'm gonna, to test for max min, I'm going to differentiate this guy again. So d squared a dr squared. So that's 4 pi minus, now once again that's r negative 2, so it becomes plus 2 comes down, that's 40 r negative 3, so I'm just got r cubed. Now what do I want for minimum? I want this value to always be positive, right? So you can see that it is, because r cubed there is equal to a positive number. This guy here is always going to be positive. So when r cubed equals to 5 on pi. Now I can sub r in, but r cubed is what I want, so maybe sub that in. Then the second derivative, dr squared equals to 4 pi plus 40 on 5 on pi, which I can conclude, therefore, d squared a on dr squared, what's that, guys? That's 8. Is it 8 pi? 8 pi, that's 12 pi, which is always positive. Therefore, minimum area when r equals 2. I guess in this question, I can actually put the exact value of cube root 5 on pi, because it doesn't actually tell me to round off. So is it meters? So maybe put a little meter there as well, and that's my answer. Not too shabby, right? 5 marks, done. Applied the framework, not too bad. So that's I'd say that's a really straightforward question for Maxima Minima. Nothing too fancy about that. Let's try another one. So this is from Balcombe Hills. So you can see that the intensity increases slightly with the formula that we're asking you to prove. They were asking us to prove. So, you know, I've seen a number of questions, and generally speaking, when they give you a 3D shape like the previous one, the two things that they deal with is volume and area. When it's 2D, generally it's area and perimeter. You can see it here, right? It's asking me to prove that the area equals to this. But they gave me that the perimeter is 18. Yep, the perimeter is 18. Now, it looks like, I mean, there's sort of square roots and stuff. Sort of feels like it might be Pythagoras. Might be Pythagoras or something, maybe not even. So let's see. Equilateral, oh, it's easier than that. Easier than that. Normally, you would use Pythagoras if it was a more complicated square root, but the fact that this is a, let me see, it's an equilateral triangle, right? What that means is these sides are all equal, which is brilliant, because this will be 2x and this will be 2x, and we know this is y. So quite simply, right, the formula, you can see, the formula that they want me to prove has no y's in it. But this shape has y in my perimeter. So what I'm going to do, find the perimeter in terms of x and y, set that equal to 18, make y the subject, and then sub it into my area formula. So step 1. Actually, let's quickly glance at step 2. Find the maximum, there it is again. You can find max or min, right? Find the dimensions. So not only do I have to find the value of x, they want me to find x, y, to find the dimensions of this window. So amazing. Okay, cool. So I know the perimeter. Oops. Highlight the tool. Perimeter equals to, now it's 2x times 3, so 6x plus 2y. Yep, and I know that this equals to 18. Yeah. So make y this, well, maybe divide everything by 2 first to make it a bit easier and a bit cleaner. And then y equals to 9 minus 3x. Beautiful. And I'm going to sub this into an equation which represents the area. Now, the area is a little bit trickier, So for area, I have a equilateral triangle where that's x, that's 2x, and obviously that's like some sort of height. To find the area here, equals to a half times the base times the height, which is just x times h. Now, height using Pythagoras would be 4 minus 1 square root, so that's like root 3h. So, sorry, root 3x rather. And I'm going to sub this into here. Therefore, just a triangle here, the area is equal to root 3x squared. Yep. So once I get that, therefore, the area of the total will be this triangle plus the rectangle. So it'll be, I mean, diagrammatically, rectangle plus triangle, which equals to 2xy plus root 3x squared. And you can see another substitution. I'm going to put the value of 9 minus 3x into this guy here and get 2x 9 minus 3x plus root 3x squared. Let's see if that's what I want. So there's 18x there, beautiful. And they factorize a negative x, beautiful. Therefore, a equals to expand that bracket. And then that's negative 6, so they factorize negative x squared out. And then 6 minus, because it's minus root 3. Awesome. So actually, that's just a quadratic later when I differentiate. Yeah. So that's 2 marks. Not too bad. Let me put a box around that. Not too bad. But can you see the framework in play, right? Yep. I have another letter of y. I need to make it subject using the given information. Once I do, get an expression in this case for area with the y in there, and then sub in the expression for y to get the final answer. So let me see if I have enough space. Space is in premium in this case. Let me just shift this up. Okay, I probably need a copy. I'll do this in the next slide. All right, now let's answer the question. So it wants me to find the maximum amount of light that would allow, so maximum area basically, right? So part 2, very straightforward. So I got a equals to 18x minus x squared times some sort of constant, right? So don't be confused by this bracket. It's just a constant. So then dA on dx, very simply is that. Bring down the 2 in front of this bracket. X, that's my derivative. Quite simple, right? I put a box around it because later on when I use it to do max min, it's linear, so I can differentiate. I use the second derivative method, not the table. So then, okay, remember, the framework says differentiate, solve, test for max min, answer the question. So set that equal to 0. If I made x a subject, so 18 equals to 2, 6 minus root 3, x, divide that over. It'll be 9 on this. I wonder if I need to rationalize. Generally speaking, I should rationalize. So, but for this question, no, maybe I'll leave it. Let's just keep going. I'll rationalize if I have to do it at the end. So that's the answer for x. Test for max min. So I'm going to differentiate this guy again. Linear goes away, x goes away, so it just becomes negative 2, 6 minus root 3, which I know, and since 6 minus root 3 is positive, right? It's bigger. It's always going to be a negative answer. So what that means is this guy's always less than 0. If it's less than 0, therefore max area when x equals to 9 on 6 minus root 3. Now, differentiate, solve, test for max min, tick, 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 answer the question. So nearest centimeter. So I suspect you need to punch this in the calculator. Let's see, 9 divided by, so that's 6 minus root 3. That's 2.11, sorry, nearest centimeter. Are these in meters? These are in meters, so 11 meters. And then they want dimensions. So this is a bit tricky because normally if it's a rectangle, you get the dimension. So is the rectangle actually the window, or do they want the diagonals as well? I guess they all they want here is the extra y, so therefore y equals to, now where's my expression for y? It's actually on the last slide, 9 minus 3x. So I'm just going to go 9 minus 3 times, I'll do the exact value and then round it off on the calculator. So 9 minus 3 times whatever the x value was. So it looks like it's 2.67 centimeters. Oh, I'm sorry, meters rather. So therefore dimensions are, I'm just going to do the rectangular dimensions of, so times a x value there. Sorry, I've got to type that again because I replaced it. Times 2, just so I can get the rounding perfect. So it's 2.42 perfect. Sorry, 4.22 meters by 2.67 meters. That's my final answer. So the framework, once again, part 1, find the equation. So quickly flick back. Find the equation to differentiate by, in this case, making y the subject in the thing that's given. Sub it into the value of y. Get the equation. Part 2, differentiate, solve, test for max min, answer the question. Let's do one more question. One more. Now, your classic questions look like this, where there's so many questions that have a 3-dimensional shape where you can either get a cylinder embedded in a cone, you can get a cone embedded in a sphere, you can get a cylinder embedded in a sphere, etc., etc. The approach is a little bit different to prove part 1, but a lot of the time they use the same sort of concepts. Whenever it's a cylinder embedded in a cone, 90% of the times you're going to use similar triangles. So to prove part 1, you can see this question actually in the HSC, wow, it's worth 7 marks. It's a bit chunky for a HSC question in particular, especially if it's not a new concept. This concept is not new. I think the hardest thing about this question is that there's no numbers, and a lot of students basically throw away marks when they see things like H and R and X and Y. They just get confused when there's too many letters involved, but it's the same thing. It's the same thing. So let's have a look. They give you volume of the cone is this, the volume of a cylinder is this, and they're asking you to prove the volume of the cylinder is this. So basically they're saying the volume of a cylinder normally is that. However, they want you to prove the volume is in terms of X only, so the H goes away. So somewhere along the lines, I need to replace the value of H with X. And if you can see it, can you see the similar triangles at play? Most questions that have a cylinder inside a cone has similar triangles, right? Where, let me redraw this triangle over here in a bigger diagram, where this is X, this is capital R, this is Y. Just be clear, that value there and there is Y, and that value there is capital H. Now, I know similar triangle basically says small on large equals to small on large. So I actually need an expression for this side here, which is obviously H minus Y. And in doing that, for part one, using similar triangles, small and large equals to small and large. So interestingly, compared to the old syllabus, similar triangles has been moved out of the advanced syllabus for year 11 and 12. However, it is expected assumed knowledge leading into the HSC and year 12 trials. So do you need to know it? Probably, most likely. I think the answer is yes. So what am I trying to do? I'm trying to make Y the subject here, right? Am I? Yes, I am. Because when I do the volume of the cylinder, I need an expression to replace this Y. So make Y the subject, so cross multiply that H, but XH on R equals to H minus Y, switch those around, therefore Y equals to H minus XH on R, and I'm just looking at the final answer. Feels like I'm going to factorize H out and go 1 minus H on R. Nope, factorize them out, didn't I? X on R. Also feels like it wants me to common denominator, so I'm just going to do that. It's almost like setting up my answer, so it's easier for me later. All right, got the value for Y. Now, volume of cylinder is, for this one, the radius is X and the height is Y. And all I'm going to do is pop this guy into this value of Y, and let me just have a quick glance. Perfect, and it's done. Therefore, what I should have done is taken that R out as well. You know what, it's not too late. Let's just do that. It just makes it a bit easier for my marker, if someone was marking my exam, to see. Take that R out, because then it looks exactly like what I have to prove. Therefore, volume is H on R. Actually, show the substitution and then clean that up. Pi R squared, H on R, R minus X. Oops. Therefore, volume is H on R, pi X squared, R minus X. Perfect. And that is 3 marks. Wow, that is generous from the HSC. Yeah. The reason why it's generous is because normally HSC has new questions where they give more marks because it's new. This one here has been done quite a few times over the last decade, 2 decades, 3 decades. So I'm surprised. So I'm just going to copy that so I can have a bit of space so I can do the next part. It removes all this junk. Let's have a look. So part 1 done. So generally speaking, the framework says differentiate, solve, test for max min, answer the question. So let's have a look. By considering the inscribed maximum volume, show that the volume of the inscribed cylinder does not exceed that. Right? So actually, this is just to bypass the word maximum. So if it doesn't exceed that, that is the maximum. Yeah, 4/9 of the volume of the cone. So it does not exceed. So basically, you want to find the maximum cylinder to ensure that it doesn't exceed 4/9 of it. So, firstly, let's do something so we know where we're headed. If it doesn't exceed 4/9, so let me highlight this in blue because I'm going to just do it in blue. 4/9 of the volume of a cone. Now, the cone's volume is fixed. The volume of a cone is going to be, and using this formula, is 1/3 pi r squared h, right? So I know in this case it's going to be 1/3 pi. Now the radius is capitalize r and then capitalize, right? So if I take 4/9 of this, right? 4 nines of this, so multiply 4 nines by this 1 on 3 pi r squared h. That gives me, what's that, 4 on 27 pi r squared h. Yeah, this is what I'm heading, this is what I'm targeting. I want to show that the maximum volume of the cylinder is basically smaller than this. It doesn't exceed this, right? Yep. So in other words, if this question was nice, the maximum volume of this cylinder is going to be exactly equal to this. So let's go there. So from part 1, so here's part 2. Yeah. From part 1, the volume is h on r, both constants, pi constant, x squared r minus x, right? That is from part 1. Now, it looks really complicated because it's got this guy and it's got this guy, all of which are constants. So all I'm going to do, you can see it's just hypercubic, right? I'm just going to use rainbows to expand that before I differentiate, just to make my life a little bit easier. So when you expand that, the r's go away, so you get h pi x squared minus h on r pi x cubed, right? Let's differentiate. So dv on dx, the 2 comes down, the 3 comes down. Guys, that's my first derivative, right? Once again, it looks pretty easy to differentiate, so I'm probably going to use the second derivative to differentiate, so I'm just going to highlight that. So, framework, differentiate, solve, test for max min, answer the question. So, set that equal to 0. Now, that's a nicely factorizable, so take out maybe the h, the pi, and the x. And I'm left with 2 minus 3 on r x. So solving this, obviously you get x equal to 0. This guy here, pretend it goes over, you get 2r on 3. Now, we want r to be a positive number, right, to give the maximum. So that guy's obviously wrong. When x is 0, you don't get a cylinder. 2r on 3, so test. 4, max min. Right, so once again, differentiate the derivative again. Yeah? You get the second derivative to be. That's linear, so 2h pi. Bring down the 2, so 6h on r pi x. So that's the second derivative. I'm hoping that when I sub this guy into here, now what do I want? I want maximum. So I'm hoping this will be negative. Right, 2/3 of that looks like it's 4. Yeah, so I think it's right. So let's say when x equals to 2r on 3, second derivative equals to 2h pi minus 6h on r pi times by 2r on 3. Now let's see if things cancel out here, right? And I'm hoping it, remember, I want maximum, so I'm hoping this answer for second derivative is negative. Now 2 on 3 times that is 4. 4h pi, 2h pi minus 4h pi is negative 2h pi, which is always negative because h and pi are both positive things. Therefore, max volume when x equals to 2r on 3. Now, test or max min, done. I'm left with one more part to the framework, right? I need to answer the question. So let me shift all this answer up so I can answer the question. So the question is, I need to show that the volume equals to this, right? So therefore, max volume, let's see if it equals to that, right? When I sub in is V. Now I know the volume of a cylinder is pi. Well, actually, no, I've got it up here, don't I? I've got it over here as part 1. So I'm just going to sub this guy, sub that into the volume and hope it gives me that blue expression. So let's see. So H on R pi x, which is 2r on 3 squared, r minus 2r on 3. Now what's that give us? Let's see. So H on R, I think it's right. Pi now, square that's 4r squared on 9. And I know that 1 minus 2/3 is 1/3, so r on 3. What happens here? Let's see. What do I want? I think the numbers all line up. Just want to make sure there's capital R there. Perfect. R, perfect. Done. So the R's go away. And then you get, therefore, volume is, I'm going to write it exactly. So 4/27 pi r squared h, 4 on 27 pi r squared h. Awesomeness. Right, which is, if you were really keen, 4/9 of volume of cone. Yeah, guys, that's the framework. So this one here, 4 marks though, just because there's that little bit of the 4/9 bit, right? So this blue bit here is worth 1 mark, but the framework still holds. So hopefully that was a good few examples, worked examples for you to understand how to approach these maximum minima questions. Over the next few lessons, I'll do a few more varied questions, and sometimes easier, sometimes harder, just to show you, give you a bit more practice on how to deal with these questions. All right, so if you like that video, please give me a like and tell your friends, subscribe. I'll see you guys in the next video.